about cyclic redundancy check codes, right? So these are the one of the category of cyclic codes as well as linear block codes. We'll see its implementation in Python. These cyclic redundancy check codes are also referred as CRC codes, and basically these are used for detecting errors in LAN communication or WAN communication. Right. So in today's session, we'll be discussing about linear block codes. Okay. What do you mean by linear block codes? Then how cyclic codes can be devised from the linear block codes. Then in detail, we'll be looking at cyclic redundancy check. So there we'll be discussing about encoder and decoder in CRC and how those CRC codes are used for detecting errors. And then finally we'll be looking at the cyclic redundancy check implementation in Python. So we'll design or implement a sender which will be sending data, and the receiver which will be receiving data, and it will be checking for whether the errors are occurred or not by using CRC codes, right? So first we will discuss what do you mean by linear block codes. So basically whenever a sender want to send any data to the receiver, so it will be transmitting that data. Before transmission, it will divide that data into uh, uh, di- uh, blocks. Okay, each block comprising uh, just for example k number of bits, and then in those k number of bits it will add some redundant bits which are referred as r. So k is the actual number of bits in data. Okay, number of bits in data. Okay, actual data. Then in those k bits, your sender will be adding r number of bits which are also called as redundant bits, and these are basically used for detecting or correcting the errors, and these bits are combined to get the actual uh, code words which is to be sent. So code word is the combination of data bits and the redundant bits, so and represent the number of bits in code word. Okay, which will be actually transferred over the network. So here in this table, these data words, so basically data word is of k bits, right? So here it is of 2 bits, right? So data word is of 2 bits. So in these 2 bits, 1 bit has been added, right? So the value of r in this case is simply 1. The value of k is 2, right? So in data words, k bits are there. So there are 2 bits, and in those 2 bits, a single bit is added, which is called as redundant bit. So it produces a code word of 3 bits. That is nothing but k plus r bits, right? So basically, the actual data which is divided into blocks, okay, message blocks, and that actual data is combined with the redundant bits to get the data to be transferred over the network. So this data word is of, in this particular example, this data word is of 2 bits while code word is of 3 bits, right? So here you can observe that if you are using 3 bits code word, right, so it will form total 2 raised to power 3, that is 8 different combinations. Okay, 2 raised to power 3, that is nothing but 8 combination. As message is of 2 bits, right, message is of 2 bits, so 2 raised to power 2 will be 4, so 4 different combination are already there in the data word, right? But if you observe the code word, out of 8 combination only 4 are utilized, because there is one-to-one relationship between data word and the code word. Okay, so there is one-to-one relationship between data word and code word. So some of the code words are not used. Okay, so these code words are called as invalid code words, right? In case of linear block codes, why these are called as linear block codes? Because whatever valid code words are there, right, if you observe, code word is of 3 bit, okay, which are basically generated by combining data words with the redundant bits, right? So if you take these total 8 combinations, so it will be 000, 001 010 011 100 101 110 and 111. Okay, so these 8 combinations are there. Out of those 8 combination, this has been utilized right there as a code word. 000 is used, right? 011 is used, right? 101 is used, right? And 110 is used. The remaining 4 are unused code words. Okay, so these are the invalid code words. So if your receiver is receiving any one of these unused code words, so it will simply rejecting that data, saying that the errors has been occurred there. So in case of linear block codes, why these block codes are called as linear block code? So if you combine any, or if you XOR any two, if you are performing XOR operation of any two valid code words, so you will get another valid code word. So just for example, if I am performing the XOR operation on these two code words, so its XOR will be 1 XOR with 0 will be 1, right? 0 XOR with 1 will be 1, and 1 XOR with 1 will be 0. So after performing XOR operation, you got 011, right? So which is already present here, which is the valid code word, right? So therefore, in case of linear block code, if you are performing XOR operation of any two valid code words, so you will be getting a valid code word, right? Again, you can observe the other, just for example, if I am performing the XOR operation of this particular code word, that is 101 and 011. Okay, so 1 XOR 1 will be 0, 0 XOR with 1 will be 1, and 1 XOR with 0 will be 1. So again, you got a valid code word here, right? When you are performing XOR of 101 and 011, okay, you got the another valid code word. So that is the property of linear block codes. Okay, if you, in case of linear block codes, if you are performing XOR operation of any two valid code words, then you will get the another valid code word. Okay, if you observe here, in this case, how this R bit has been added into the code words, right? How that R bit is appended to the data word. So in this case, it has been decided as per the parity check. Okay, so parity check of the data word. If it will be making the even parity there, even number of ones should be there in the data word. If even number of ones are there in data word, then 0 will be added. If odd number of ones are there, then 1 will be added as a R bit, right? So if you observe here, right, in this case, you can see that the first data word is 00, which is to be sent, right? So number of ones are 0, that means it is having even number of ones, so therefore 0 is appended to that data word. But here odd number of ones are there. To make it even number of ones, this one has been added there in the data word. Similarly here, odd number of ones are there. To make it even, this last bit will be changed as 1. Here already even number of ones there, so therefore last bit is 0. So this is nothing but what? Parity uh, check. Okay, so as per parity check, the code words will be generated. The value of the bit to be added will be decided. So in this case, as we have seen, the value of n, that is the length of code word, is 3 bits. The value of actual data to be sent, it is of 2 bits, right? And the number of redundant bits as taken as 1 bit, single bit. Okay, so now let's look at the cyclic codes. Okay, so what are the properties of cyclic codes, and how these had been derived from the linear block codes. So in case of cyclic codes, obviously the property that we have seen in the case of linear block codes, that means whenever you are performing the XOR of two valid code words, you will get another valid code word. Okay, so that property is also possessed by the cyclic codes, along with one more property. So what is that property? So whenever you are shifting or rotating the code word, if you are performing left shift operation on the code word, left shift operation on the code word, so you will get another valid code word. Okay, the first property of linear block code is possessed by the cyclic code itself. That means if you are performing the XOR operation of any two valid code words, so you will get another valid code word. But before that, if you observe this table, the value of k here, that is number of bits in data word, are 4, right? 4 bits are there. In case of the length of code word, if you observe there, so it is of 7 bits, right? So total 3 bits has been added in the data word to generate these 7 bits of code word, right? So the property possessed by the linear block code is also possessed by the cyclic codes. If you are performing the XOR operation of any two valid code words, so you will get another valid code word. Just for example, here if I am XORing these two code words, so its XOR operation will be, I'm performing XOR operation, right? So it will be 0 XOR with 1 will be 1, 0 XOR with 1 will be 1, 1 XOR 1 will be 0, 0 XOR with 1 will be again 1, and there are triple 1, triple 1, so it will be simply triple 0. So you will find that this particular code word, that is 0001011, that is 0001011, is already present in this table. That means it is when you are performing the XOR operation on the valid code word, so you are getting another valid code word. So this is the property of what? Linear block codes, right? So one additional property possessed by the cyclic code is that whenever you are performing left shift operation, left shift operation, so you will get the valid code, right? So just for example, if I am performing the cyclic left shift operation on this particular code word, right? So obviously this particular 0 will go to this position, right? If I'm performing cyclic left shift operation, right, on this particular code word, this 0 will go at this position, and all remaining bits will be shifted by 1 bit position to left, right? So you will get the code word as 0 0. Okay, so these bits will be taken as it is initially, 0 0 1 0 1 1 0 0 1011, and this first bit will be added at the last position. Okay, so you get after performing the cyclic left shift operation on the selected code word, so you will get another valid code word. So you can observe this code word 0010110. Okay, so here this code word is present. Okay, so that means if you are performing cyclic left shift operation on the cyclic code, so you will get another valid code word, right? So that is the additional property of the cyclic code compared to the linear block code. So cyclic code are the one of the category of linear block codes. Basically cyclic codes are linear block codes, but with that additional property, that is whenever you are performing left shift operation on it, uh, cyclic left shift operation, so you will get the valid code word. Now let's discuss about the cyclic redundancy check. So this CRC codes, it is one of the category of, or it is one of the form of the cyclic codes, right? So under cyclic codes there are other types of codes as well, right? So one of the category is the cyclic redundancy check codes. So these are used for checking the errors. Preferably these CRC codes are used in LAN and WAN communication, right? So wide area network and local area network, these CRC codes are used. So in case of these cyclic redundancy check codes, uh, at the sender side you have an encoder, and at the receiver side you have decoder, right? So as you can see in the previous table, the length of data word was 4 bits. Okay, so just for example, if we are extending that example, so we have taken the length of data word is 4 bits here. Okay, so we have taken it as 4 bits. So what that sender will do, sender will add three redundant bits into that data word, okay, to generate a code word of 7 bits, right? It is not necessary you should take same number of bits here. Data word may be of 4 bit, 8 bit, 5 bits, 6 bits, 7 bits, anything, okay. But depending on what divisor you will select, according to that these redundant bits will be generated, okay. So sender will add these redundant bits, okay, into the data word to generate a code word here, okay. So how those bits are generated, which is to be appended to the data word. So basically sender will initially append number of zeros, right, depending on the size of divisor, okay. So if divisor here, this divisor is selected, okay. So in this case divisor is selected, it is of 4 bits, right, as you can observe d0, d1, d2, d3. So it is of 4 bits. So this common divisor will be shared by the sender as well as receiver. So uh, this divisor will be present at sender side as well as the receiver side, okay. Same divisor will be present at both sides. So depending on number of bits present in the divisor, these number of redundant bits will be appended into the data word. So initially all those bits will be selected as zeros, right? So as divisor is of 4 bits, so therefore redundant bits will be of 3 bits, correct? So how this divisor will be selected? So basically you have to decide the number of bits in the code word minus number of bits in the data word which are which is already known, right? How many bits are there in the data word? You will decide how many bits will be there in the code word, and then you will add 1 into it. So as you had decided, or it is known that there are 4 bits in the data word, and you if you require a code word of 7 bits, right, then your divisor will be of 4 bit, that is 7 minus 4 plus 1, okay. So that is the standard equation to decide the number of bits present in the divisor, right? So just for example, if I want a code word of 8 bits, right, as here you can see that, you can observe that total number of bits in the data word are 4, right? So equation for calculation of number of bits in the divisor will be, again it is the same equation, and minus k plus 1, as there are 4 bits, right, 4 bits in the data word, that is the value of k is 4, right? But if I want the code word of, just for example, 9 bits, right, so it will be 9 minus 4 plus 1, okay. So the number of bits present in the divisor will be 6, right? So divisor will be of 6 bits. But as you can observe in this particular diagram, we are simply adding uh, the 3 bits in the code word, right? So total number of bits in the code word will be 7 bits. So therefore the number of bits in the divisor will be 4 bits, okay. So what sender, that is the encoder present at the sender, will perform? So depending on number of bits to be appended and depending on the size of code word, it will append number of zeros to the data word to get the same size of the code word, and then this generator will perform modulo 2 division operation on this particular uh, data, right? That is a3, a2, a1, a0 followed by 3 triple zeros, right? So this will be divided by this selected divisor, right? And after division you will be getting some remainder. You will be skipping the quotient part. After division you will be skipping quotient part, and whatever remainder will be there, remainder will be of again 3 bits, and those remainder 3 bits will be appended to generate the code word from the data word, right? So this code word then will be transferred to the receiver where the decoder is present, right? So what that decoder will do now, this divisor, okay, selected divisor is shared at share at both sides, that is it is available with sender as well as receiver. So the receiver, that is decoder present at the receiver, will perform again division operation, right, on the received code word. So whenever you are dividing the received code word with the shared divisor, so remainder should be 0 if data is correctly received. So that remainder here is represented as the syndrome, okay. So if data is correctly received, so in that case this syndrome should be 000, right? So if this syndrome is 000, so in that case data will be extracted from the received code word, right? Otherwise, if this syndrome is not 000, right, so in that case data is corrupted, so that data will be discarded. Okay, so that is the simple logic uh, in the cyclic redundancy check, where the encoder present at the sender side, decoder is present at the receiver side, will be designed to implement the logic of the cyclic redundancy check codes. So let's see example here so that all these things will get clarified, right? So as you can see here, this is the encoder. Okay, this encoder is present at the sender side, right? So as you can see that currently we want to generate a code word for this data word, that is 1001. Okay, so if I want to generate the code word for this data word, so initially I will be appending 000 to this data word. So here you can see that the same data word is there, 1001, and 000 are appended to this data word, right? Now I will be selecting one divisor. That divisor will be shared to sender as well as receiver. So here divisor is selected as 1011, correct? So how this divisor is selected? So because I want a code word of n bits and the data word size is k, so therefore the divisor size will be n minus k plus 1. So I want 7 bit of code word, data word size is 4 bits plus 1, so divisor will be of 4 bits, right? So therefore 4 bit divisor is selected. So here 1011 has been selected as divisor. Now modulo 2 division will be performed, right? So as you can observe here, the first bit in this available dividend is 1, right? So therefore 1 will be taken as the first bit in the quotient, right? So if you multiplying this with particular divisor, selected divisor, so it is 1011 here, correct? If you are multiplying it with this 1, why you have taken it as 1? Because the first bit in this particular dividend is 1. So whenever you are performing multiplication operation, then a multiplication is performed as per the AND operation, and in division you know that subtraction will be performed, that subtraction will be performed as XOR operation, right? So here it has been multiplied with 1, so 1011 has been written here. Now subtraction will be performed. Subtraction is nothing but simply the XOR operation, right? So 1 XOR with 1 will be 0, 0 XOR with 1 will be 1, 0 with 0 will be 0, and this will be simply eliminated, right? So then again next bit has been taken from that dividend, so it is 0, so here that 0 has been taken. Again you can observe here this first bit here is 0, so therefore now you will take the quotient bit as 0, and then again this 0 will be multiplied with this divisor. So if you are multiplying, that means if you are performing an operation with the divisor with 0, so you will get all zeros, right? Again XOR operation will be performed here, right? So here this XOR will be 0, here XOR will be 0, here 1 XOR with 0 will be 1. Again these bits will be simply discarded. Again next 0 will be taken from the dividend, right? Here you can observe the first bit as 1, so therefore you are taking it as 1 in the quotient. Again you are multiplying this one with 1011, so it is 1011. Again XOR will be performed, right? So 0 XOR with 1 1, 0 XOR with 1 1, 0 0 0, and this will be discarded, right? The last bit will be taken, correct? Again here you can observe it is 0, so therefore quotient bit has taken be 0. So if you multiply it with, so you will take 0. So 0 0 0 will be the XOR, 1 0 1 will be the XOR, 1 0 1 will be the XOR. This will be discarded. So this is the remainder. Okay, this is nothing but the remainder. So whatever quotient you are taking after performing division operation, this division operation will be performed by the code encoder to generate code word from the given data word, right? So now this quotient will be discarded, and whatever remainder has been computed, right? So that will be combined or appended to the given data word. Data word was 1001. Okay, so 1001 was the data word. Now that remainder has been appended, that is 110, to get the actual code word, right? So for 1001 data, you have the code word 1001110. You can also observe that in the previous table. Okay, so 1001 was the data, right? So 1001 110 remainder was generated there, right? Correct. So this is how your encoder will generate code word from the data word. Now this data word will be sent to the receiver. Okay, so simple data word will not be sent. Data word combined with those redundant bits, which will be used for checking the errors, right? So combinedly those will be called as code word. So that code word will be transferred to the receiver. Now let's see what that receiver will be doing, right? So here at the receiver side, you can see that there are basically uh, the receiver is also has the divisor which sender has. So sender has the divisor 100. So same divisor will be utilized by the receiver, that is 1011. Okay, so 1011 was the divisor used by the sender for computing code word, right? So same divisor has been used by the receiver here. Now here two cases has been taken. One, the code word has been received as it is. So as you can observe there, 10011110 was the code word, right? 10011110 was the code word which has been sent by the sender. So the same code word has been received. And another case has been taken here, which is the corrupted code word. So here this bit is corrupted. Okay, so it is converted to 0 here. So this is invalid code word received. This is the correct code word or uncorrupted code word has been received by the receiver. Now what that receiver will do? Okay, so with the same divisor it will perform the division operation as we have seen on the previous slide, right? In same with same operation, that is modulo 2 division will be performed here, right? So this code word will be taken as it is, that is 1001 triple 10, right? So this will be taken as it is, and 1011 divisor will be utilized. As you can observe there, first bit is 1, so quotient will be taken as 1. So 1 multiplied by this 1011 will be 1011. And similarly again XOR operation will perform 1 XOR with 10, 0 XOR with 1, right? 0 XOR with 0 will be 0. So these are bits discarded. And similarly remaining bits in the code word has been taken below for performing or completing the division operation. And after performing division operation, if you are receiving code word in uncorrupted form, so the syndrome will be 000. As you can see that syndrome means it is nothing but the remainder, okay, that you received after performing the division operation. So if remainder is 000, that means syndrome is 000, that means correct code word has been received. So the uh, these redundant bits will be removed from the code word, and the actual data word will be extracted from it, and those will be accepted, right? But if in the received code word some bits has been corrupted, so obviously after performing the division operation with the divisor, you will not get this remainder as 000. Okay, there will be some non-zero bits in the remainder. So if syndrome is not 0, so in that case simply data word, received data word will be discarded. So this is the process followed by the cyclic redundancy check method. Now let's see the implementation of this CRC code in Python. So again, for implementation purpose, I'll be uh, implementing one sender. Okay, so and one receiver. So there will be separate code for sender. So I will be saving that code as sender.py, and receiver will be indicated by receiver.py, and I will be executing in anaconda, right? Anaconda prompt. So you have to open that anaconda prompt. Simply you have to do it as run as administrator, right? Simply by okay. So here I have already created a directory with name crc, right? So in the under that crc I will be creating two separate file. One will be holding the sender side logic, right, which comprises the encoder, right? So I'll indicate it as sender.py, and another code file I'll be indicating is simply as receiver, right? So receiver.py, correct? And I'll just right click on it. I'll open it with notepad. You can open it with any Python editor, but I'll prefer to open it with notepad. Okay, so here I will simply add the sender code in that file. I'll just elaborate what that sender code is doing, right? So simply this code used for sender can also be considered as code for the client, right? So in today's session we'll be also learning how client and servers are communicating. So this sender is nothing but the client, and the receiver will be your server, right? So receiver will be the server acting as a server, while your sender will be acting as a client, right? So I need to open two separate anaconda prompts, right, to run the sender as well as receiver, right, simultaneously or parallelly, so that whatever sender or client sending, your receiver or server should be able to receive it, right? So now these two codes has been saved in these files, or which are also called as Python script. Now I should switch to this directory, right? This directory where the code has been stored. So it is on G drive. So initially I will simply move to G drive, right? So I just switch to G drive, and I will go under that directory, right, where the code has been stored, and here I will execute the command python sender.py, right? So this should get executed, right? So here you can see that this particular no connection could be made because the target machine actively refused it, right? So here you can also open the another prompt, anaconda prompt, okay? So where your receiver should be there, correct? So again I will go to the G drive. I'll go into the directory where code is present, right? Then I will execute python. Here I have executed sender, right? Sender.py. Here in another prompt it should be receiver.py. Okay, so here you can see that this receiver is acting as a server, Okay, so it has been started, the socket has been created, it is binded to this port, that is 12345. You can take any port. Now socket is listening, so whenever client tries to, or your sender tries to connect to that port, right, send any data to the server, your server will establish connection with client through this port, that is 12345. And here the port address, sorry, IP address has been taken as 127.0.0.1, while port address is 12345. So this is the local system address, right, IP address. Okay, so if I'm doing it as python sender.py, now connection will get established, right. Now you can see that this connection has been established, and here you got the message, got connection from 127.0.0.1 to 2506. Okay, so it is communicating through this particular port, right. So now let's look at what these codes are doing. So I will initially explain the code for the uh, your sender. Okay, so here we are using the library socket from the python, right, because here we are simply implementing sender as client and a receiver as the server, right. So client server communication is there, so you should establish the socket connection between your sender and receiver, right. So actual execution of this code, if you observe this complete code for the sender, so the first is the function has been defined here. Okay, this will not be directly executed until and unless you doesn't call that function. So this function is used for performing the XOR operation, right. I will just explain it. Then next one is for performing the modulo 2 division operation, as we have seen in the presentation. Okay, so it will perform division using modulo 2, right. Next function is used for encoding data, right. So as you can see that initially the data is appended with the 000, and then after computation of remainder it will be appended with the remainder to get the actual code word. So this function is used for getting the code word. Now the actual execution of program will start from here. Okay, that is sender. Okay, so from socket I'm just calling this particular socket, right. So the instance will be created in S, and here port has been taken as 12345. So the connection will be established using this socket reference, using this connect method, where I will be passing the IP address of the server, and the port will be used for establishing the socket connection. So here port has been used as 12345, as this is the sender code, right. So next it is asking for entering the input string. As you can see that in the sender.py, right, sender.py, it is asking for enter data you want to send, right. So the same message has been displayed here, enter data you want to send. Okay, so you can also use print function here to display this message, and then by using input method you can read whatever user will enter there, right. Also you can pass directly the string message to the input function, so this string message will be displayed as it is, and whatever user will enter on this anaconda prompt, that will be read by the input function, and this will be assigned to the input underscore string, right. After that whatever now as you can you can observe there in the presentation, whatever data that we had taken as the data word, code word, all those in the binary form, that is in the form of zeros and ones, right. But here user can enter any string message, any digit message, or anything else, right. So that should be converted into binary, right. So that will be done with this format ord of x function. Okay, so whatever input has been entered by the user, that is read by that input has been read by using input function and assigned to the input string, and using this for loop, whatever number of characters are there in input string, right, all those characters will be converted into the binary representation, right. So basically Here simply your character data, right, one by one will be converted into a binary string using this format, and all those will be joined. Okay, all those will be joined in the sequence and it will be assigned to the data. So this can be observed here. If I enter any input here, just for example, I will say hi. Okay, I want to send hi there, hi, right? So there are two characters here, so those two characters should be converted into the binary form. So that will be done by using this particular function. Okay, that is format d of x. It will be converted into binary, right? So there are only two characters, so initially h will be converted into binary and then I will be converted into binary, right? So hi was the message hi, and then the first binary conversion will be joined with the another binary conversion, and that will be assigned to data. So here you can observe it. I have pressed hi, so here the complete has been processed here, but here you can see that whatever data I have entered hi, it has been converted into this binary. So for a single character, okay, for a single character, 7 bits has been used, right, for representation, correct? How many bits has been used for single character? 7 bits. So for h, 1101 000 is the binary representation, and for I, 1101 000 is the binary representation, correct? So after converting that into binary, it has been assigned to data, and then message has been printed. What is that? Enter data in binary format. So here you can see that the data has been printed, that is enter data in binary format is this one, right? So that data was assigned to this data, and here it is accessed and it has been printed, right? Just a minute. Okay, so here we have taken, as in the previous slide we have seen that divisor should be selected, so here we are selecting divisor as 1001. Okay, so in the data that has been converted into binary, we have seen that for each character the 7 bits has been used, right? For each character 7 bits has been used. So as divisor is 4 bit here and data is of 7 bits, right? So the in the code word 3 additional bits will be added, right? How many bits will be added? 3 additional bits will be added, correct? So here instead of considering it as simply the word of 7 bits, so it is combinedly it is of 14 bits basically. I mean, it is 14 bits. So the code word size here we are taking it as 14 plus 3, that is 17 bits, right? So your divisor will be of 14, sorry, 17 minus 14 plus 1, so that will be of 4 bits. So here a divisor has been selected as 1001. Now after selecting that divisor, the answer is calculated here, right? So that is nothing but the encoded data to be sent, right? Encoded data is nothing but your code word, right? So that will be identified from the actual data. Actual data is of 14 bits here, right? And divisor, which is of 4 bit, has been passed to this encode data function, and this encode data function has been defined here, right? Here you can see the definition of encode data, where the data of 14 bit has been passed, divisor is 1001, right? So 14 bit data and 4 bit divisor has been passed here. So the length of divisor will be 4 bits, right? So L underscore divisor will be 4 bit will be assigned here, so 4 will be the value of L underscore divisor. Now as you can see in the encoder, depending on the divisor size, the number of bits will be appended. So how many bits should be appended there? So 3 bits. So initially 3 zeros will be appended to the 14-bit data. So for that purpose this statement has been added. Okay, so how those will be appended? So data will be of 14 bits, right? and you are appending simply zeros. But how many zeros will be appended? So the L underscore divisor is 4. 4 minus 1 will be 3. So 3 zeros will be appended to the data. So your appended data comprises 14 bits and followed by the 3 zeros, right? Now this appended data will be passed to this operation. After appending data, after appending 3 zeros to the data, as we have seen the logic of CIC, it is performing division operation, right? With the selected divisor. Now appended data is of 17 bits, right? That is 14 plus 3, 17 bits, correct? Now that appended data has been passed here along with this divisor of 4 bit. Now this function has been called. Again, this function has been defined here, modulo to division, right? So this should return the divisor. So here this data module in the definition of modulo to division, so that data of that is appended data of 17 bits is there and your divisor is there. Again, the length of divisor will be selected, so it is 4 bit. Okay, divisor will be of 4 bit. Now your dividend, you are selecting some number of bits from the dividend to perform the division operation. So how many bits? Depending on the size of the divisor. So there are 4 bits in the divisor, so only 4 bits initially selected from the dividend out of 17 bits, right? That is nothing but this dividend is nothing but the appended data. So first 4 bits will be selected, and depending on that first 4 bits, right, till this particular while loop will be repeated. So for every 4 bit combination, right, for every 4 bit combination, this while loop will be repeated, correct? So what is the purpose of this while loop? So it will perform simply the XOR operation, and depending on that XOR operation, it will calculate the remainders, right? So as you can see here, till the total length of dividend is less than the what you have selected, that is nothing but 4 bits, initial 4 bits. So if this particular first bit is 1, right, of time, as we have seen that if first bit is 1, so you are simply taking divisor as it is, right? You are multiplying it with 1, that is nothing but you are performing add operation as we have seen in the slide. Okay, so here as you can see in this slide, if first you are talking about the encoder, okay, as the first bit is 1, so quotient value is selected as 1, and you are just taking this divisor here, which is nothing but the multiplication of 1 with 1. So divisor is selected as it is. So same thing has been done there, right? So if it is 1, so you will be passing this divisor and temp is nothing but those 4 bits, first 4 bits and the actual divisor, right? So the XOR operation will be performed on that, and then remaining dividend will be appended to it, to the temp, right? So this XOR function is again defined here at the very beginning. So what that XOR is doing, so simply whatever has been passed here, now what you have passed, so you have passed the divisor and the first 4 bits, right? First 4 bits, correct? So as you can see that divisor and the temp has been passed there, correct? Temp comprises the first 4 bits. Why 4 bits? Because the length of divisor is 4, right? Okay, so those two things has been passed, that is divisor and the 4 bits from the dividend or the appended data. Okay, so depending on the length of that dividend, this for loop will be repeated, and one by one XOR operation will be performed simply by comparing the bits in the divisor and the dividend. Okay, so if both bits are same, so XOR should be 0, and if bits are different, then XOR will be 1. Okay, so depending on that, the XOR result will be added into this empty result, right? so 0 and 1 will be appended into it, so obviously those will be joined here in the result, correct, and that result will be returned to that function. Okay, so whatever result is there, correct, so that XOR operation result plus dividend of next bit. Okay, so next bit will be selected from the dividend, and whatever result is there, that will be assigned to temp now. So likewise this logic will be repeated, right, and if bit is first bit is not 1, right, if it is not 1, so that means it is 0, so if it is 0, so all zeros should be there, right, so for that purpose this else statement is used here, right, so all zeros will be taken there, right, and then the actual data present in the dividend is passed, right, so as you can see that these are the all zeros present as the first argument, and data from the dividend has been taken, right, so this is nothing but data from the dividend, right, and these are the all zero, and then their XOR operation will be performed using the same logic. So same logic will be used to generate again that result. Those result will be returned here. Again the next bit has been taken from the dividend. Okay, so this process will be repeated, and the value of peak will be incremented, right, until what, the total bits from the dividend has not been taken in the next division process. So how many bits are there in the dividend? Total 17 bits are there. So still the value of peak is 16. This while loop will be repeated, right. Once it is 17, the while loop will be terminated, right. So after this, so you have performed the operation, and now temp is comprising the results basically there, right, correct. So now you will be checking whether the temp first bit is 1 or not. If it is 1, then again you are performing XOR operation on divisor and temp, right. Again actual divisor will be taken and actual data will be taken there for performing the operation, and then your temp will be generated on it, correct. So this is nothing but the last bit operation performed there, and then this temp is assigned to what, check word. Now this check word will be written by this mod 2 division. This check word now comprises simply the remainder basically, right, it comprises remainder, and that remainder has been identified here by performing the uh, XOR operation on a divisor, and the identified that particular data, right. Okay, so simply this remainder is written as check word in this particular function. Okay, so here you got the remainder. Now you have actual data, right. What was that actual data? Data was of, that is appended data of 17 bits. So 17 bits plus remainder. So you got the remainder. Remainder here was 3 bits. So that has been appended with the 14 bit data. Okay, data here not appended data. Here actual 14 bit actual data was there, right. Appended data was passed to the modulo 2 division. Good. So 14 bit data now appended with the 3 bit remainder, and final code word has been generated. So code word will be of now 17 bit. Initially that was appended with 3 zeros. Now it is appended with the actual remainder. That remainder has been returned by the modulo 2 division function, right, that we have just seen, modulo 2 division function. So it has been written as a check word, that is nothing but the remainder. Now once that has been returned, right, to this particular it has been okay, this encode data will return that code word, right. So encode data, assign that code word, which is the combination of data and the 14-bit data and the check word, that is nothing but the remainder of 3 bits into answer. So answer comprises now 17 bits, which is nothing but the code word. Now that code word here, you can see that encoded data to be sent to the server in binary format. That message has been will be displayed, that is encoded data to be sent to the server in binary format. So the first 14 bits you will find similar to what your data comprises, and to that this particular remainder has been added, that is like a 3-bit remainder, that is 100, right? So this message is displayed here, correct? Right. Now this data we want to send to the receiver. So for that purpose you are using this socket connection S, right? And you will send data by using send to function. For that purpose you will use answer dot encode. So what this is predefined function. Okay, so it works with the strings, right? So what that encode will do, encode function will convert string into byte code, not binary. It will convert it into byte code, because whenever you are sending data over the socket, it should be in bytecode format, it should not be in string format. So therefore this predefined encode function is called by using this string variable, that is answer. So answer comprises 17 bits of code word, right? So those code word will be encoded, string will be converted into bytecode, and then it will be sent to this particular address over this particular port, that is 1 to the 4, right? Now here your server, as your server is listening, that is nothing but your receiver is listening. So now this code of receiver will be used. Here also we used import socket, same XOR function is there, right? Because as you can see that division operation is also performed by the receiver, not only the sender. Now what receiver is doing, receiver is receiving data from the sender, correct? After receiving that data, it will divide that data, perform the division operation using the same divisor available with the sender, correct? And after that it will check whether the remainder is 0 or it is non-zero. If remainder is 0, then data is correct. If it is non-zero, then it is incorrect. So therefore for performing XOR operation, same function has been defined, which is defined in the sender. Same modulo to division function has been defined, which is also same as the function available in the sender. Okay, so I'll skip the explanation of these two functions. Again, the decode data function, as there was the encode data function, here we have decode data function. Okay, so from here the actual execution of the receiver will start. So as you can see, the first statement where the socket reference has been taken, and the first statement printed was socket successfully created. So if this statement has no error, then automatically this message will be displayed, right? Now port has been taken 1 2 3 4 5, the same port that has been used by the sender, and we are binding the connection here to that port. Okay, so whenever your sender will be sending data, so through this port your, because your receiver is binded to that port, therefore whatever you will be sending through that port, that your server will be listening to it. So after that, after binding, you have printed this message socket binded to, right? So here you can see this message, right? Socket binded to, okay, and the port number, that is 1 2 3 4 5, right? So whatever port that you have taken, and it will be listening, right? So 5, that value has been passed, so it will pause for that particular time for listening through the port, right? So after every 5 units of time, it will be again listening to it, right? And here you can see that socket is listening has been printed after that, right? So that is the simple logic to create a server, right? Now until and unless your server is on, that is receiver is on, right, these statements will be continuously executed. Now currently, as you can see there, execution of our sender has been terminated, but still your receiver, that is nothing but server, is under execution, because again if you execute the sender.py, again some messages will be displayed, right? Connection will be established there, correct? So your server or receiver is in listening mode, right? So what has been done here? So connection and address has been fetched through the method accept. So it is from the socket, right? As dot accept, so it will be accepting that connection, and address has been passed, so which address will be used? So you can see that got connection from address. Okay, so that message had been displayed there, right? So got connection from that particular address, right? So that address has been displayed there. And C comprises the connection, right? Now on C you are receiving data, that is 1024 bytes of data, right? There we have encoded data, right, by using encode function. As you can see there, answer send to. So whenever this send to function will be executed by the sender, so here it will be received, right, in the receiver. So receiver will be receiving 1024 bytes of data, right, and that will be assigned to data. Now after receiving data, it will be decoded, that data will be decoded. Now it is bytecode, so it will be converted into string again, right? So therefore here it has been this message has been printed, received encoded data in binary format. So you can see on the uh, receiver side, received encoded data in binary format, right? So it was sent as the bytecode, so bytecode will be converted into string by using decode function on the data, right? So this is nothing but the strings of one and zeros, right? So this string has been printed there. After that, here if you are not receiving data, so automatically your receiver will be terminating, or it is again listening it. Same divisor has been selected here, 1001, which was available with the sender, right? Now again here you will be decoding data. At the sender side it was encode data, here you are decoding data, you are passing the actual data, right? Now here data will be of actual 17 bits, right? So 17-bit data has been passed along with the divisor of 4-bit, right? Now this decode data function will be called, right? So again decode data as per the divisor length, number of zeros are there, right? So decode data has been received here, those zeros will be appended there, right? And then again this modulo 2 division will be performed, correct? And then this the same logic is used for this modulo 2 operation, modulo 2 division operation, as I have just explained it. Okay, so you just go through it. And under modulo 2 division operation, XOR operations are also there for performing this subtraction, right? So XOR function is again same as that has been defined in the sender, right? So it will obviously return the remainder. So once it return the remainder, so that remainder will be received here, and it will be verified that remainder is 0 or not, right? So that you can see that after that you got this remainder after decoding, so that will be printed here, right? So here you can see that remainder after decoding is 000. So as 000 is there, right, as it is 000, so there is no error, right? And that has to be sent as an acknowledgement to the uh, sender, right? So for that purpose next logic has been implemented. So here 0 has been taken, length of divisor -1, so 000 will be generated here. So answer is equals to temp is equals to that, right, 000, and that will be sent to the sender. Okay, so this thank you data, because you have used send to, as we have used send to in the sender, now you have used send to in the receiver, right? So this message will be printed, thank you data. So data dot decode will be there, so same data will be printed. so no error has been found. Okay, and again this was, before sending it, it should be decoded, encoded, right? So this string will be converted into bytecode and it will be trans transferred to this particular address over the port. So this is the address of your sender, and it is listening to this port 12345, right? So same thing has been printed here, as you can see there, received feedback from the server. Okay, this has been listening basically, right? As you can see that in the next statement, in the sender, right, it is sender.py, received feedback from this here, and it is receiving now as dot receive, and it will be decoded. That byte code will be converted into string now, right? 1024 bytes will be received, right? So the same thing has been specified here, send to. So this message will be sent to the sender, right? Here it is receiving it through this receive function, right? So this will be sent, and now this will be printed. So here this thing has been printed, received feedback from the server, thank you, data will be printed and received, no error found, right? And if it has, if you are this, here you are comparing basically, right? This was the remainder generated by the decode data function. If it is 000, right? So you are comparing it with this temp, right? Temp, you have generated 000 here. Temp will always comprise 000. Answer is actual remainder, right? If it is non-zero, right, answer, your current remainder is not 000, then else block will be executed, where it will be sent that error in data, and it will be displayed on the sender side. Okay, so this is how the logic of the CRC code has been implemented, right? So the only difference in the receiver side is that the uh, your 14-bit data has been selected along with the divisor for performing the modulo to division operation and the computation of remainder. But after computation of that remainder will be checked with the actual number of zeros in the data. Okay, that is nothing but the remainder should be zero only. If it is zero, then no error will be there, and if it is not zero, then error will be there. Okay, so that is how you can implement the CRC code in the Python, right, for checking the errors in the transmitted data. So thank you.